Okay. So how about I want the arc length function as a function of y. Where's Yanni? Dong. Where's Yanni? So did you get that? So what would that arc length function be as a function of y? Okay. Okay. And then is that square root? Is that the arc length function? The square root? Does that give us the arc length function? That's rate of change. Okay, so that's the square root is the rate of change function, 1 plus, okay, and then how would we get the arc length function? Walker, you're up. Okay, right. And since we're doing it with y, we'll just keep it with y. So right, it'll be the integral from a to y, and we'll call this little s. Integral from a to y, 1 plus, what Yanni said, 1 plus the derivative of the g function, and we know it's that square root part is the rate of change. Okay, so now we want to graph this function as a function of our independent variable y. So we want to graph arc length as a function of independent variable y. I'm going to put this over here on the right, and I want to put our independent variable y on the horizontal axis, and then I want to put arc length on the vertical axis. So how do I tell GC to do that? Where's Micah? Micah Stewart. How am I going to tell GC to graph this function with y on the horizontal axis and then the arc length on the vertical axis? Okay, so what would I write in? Can you tell me what I would type in? Okay, so yeah, so now he's saying to get our independent variable on the x-axis and GC, we want to use x, right? But we know for us, we know that x-axis is going to represent the y coordinates. So how about, where's Jerome? How am I going to get that function on this graph over here with y horizontal and arc length vertical? How do I graph anything? So how would I graph anything? Y equals the function, right? So I'm going to do y equals this function, and what am I going to put for my arguments there? So we know where does this curve start? Y equals 1. So it's going to be y equals SG of what? 1 comma. So it'll be y or x? It'll be x, right? It'll be x. Now you can ignore the apostrophes, if you remember. The apostrophes don't have anything to do with derivative. That's just GC's way of saying do it in the new window over here. Okay? So it's the same thing. Y equals SG. I'm going to start at 1, and then where my independent variable was in the definition of the function y, I'm going to put x, so it puts that independent variable on the x-axis. Does it make sense? All right, and so when I graph this, what is it going to look like? So can we predict in general, what this, and not just remembering the answer that you got if you know you got it right, but how can we reason about what this arc length function is going to look like? Where is Jake? Yeah, can you kind of give me a feel for maybe what's going to happen when I turn on this graph? So horizontal line. What do you think? Let's see. Where's Pingfeet? Pingfeet? You agree with that? Horizontal line? Okay, so what would you say? The arc length function. So let's talk about when y equals 1 here. We get the point 1, 0, right, on this graph. So what about our initial point of arc length over here? So the correspondence point for arc length that corresponds to this point on the graph of G, 0, 1. What would our initial point over here be, and why? Where's Samantha? Samantha here? See, I'm going to start learning your names, and then you can't hide anymore. Where's Zach Hansen? Yeah. So we're accumulating arc length. What? Starting from here, going which way? Left or up? Up, right? Because our independent variable is y up here. So we're accumulating arc length starting at 1, going up this way. So that means at the beginning, what's our ordered pair in the arc length function? What comma what? 1, 1. Agree with that? So an ordered pair would be, hello. There we go. Okay, so an ordered pair would be a value of x and then a value of x comma s sub g 1 comma x. That's what all the ordered pairs will be like. And remember this, now, so this x is our x-axis here, but it's really our independent variable y for this graph, right? So this is the independent variable y. So when we get started, we're at the beginning of the curve. What's the ordered pair that we're going to get at the beginning of the curve? What comma what? 1, 0, because we're starting from 1, right? And then when that value y is 1, what is the arc length? 0, like this. Okay, and then what's the independent variable going to do? It's going to, you said, go up, and as it goes up, we're going this way here, right? This is our y value. It's over here, it's a y value. And what will happen to arc length as y increases? So as y increases, arc length will do what? Increase. So maybe something like this. Question? Is a question? Yeah.
Why did you switch? Because initially we were looking at g of y.
Right.
Why did you go to, when you graphed it, graphing it with y on one side and x value?
You can do it any way you want.
Okay.
So I was picking the most, so when we graph functions, 99.9% of the time in your past, you graph dependent variable on the vertical axis and independent variable on the horizontal. So I stayed consistent with that.
Okay.
Does that?
So it's not technically incorrect.
You could do it either way. So if you want to put your independent variable, keep it on y, well then your arc length would be the x coordinate,
Right.
and that's okay.
Flip it.
And that's okay. And you know, ideally we should be able to interpret it either way. But I'm just keeping it here to be consistent with all graphing most of the functions you've done in your lifetime, because this is hard enough, right? It's hard enough to see that our independent variable y here, now we're going to put that on the horizontal axis, and then our y value on this is going to be arc length. Okay, yeah, questions?
What is the above the x there? Is that x to the negative first on that?
No, those are just apostrophes, which you can ignore. The apostrophes in GC just are opening up a second window pane. So just all that is, all those apostrophes, y apostrophe, x apostrophe, is just so telling GC, do it in another new window. So when you look at that, all you have to think is y equals s of 1 comma x. Forget about the apostrophes. So that's not derivative. It's just GC's way of allowing you to graph on a second set of axes.
So in this case, we're not taking like the original function and putting it in terms of y, so we're not taking the inverse of it this time. It's just so.
What do you mean? So ask me again.
So like in the previous problems that we did with like the shells and everything, whenever we were using y as an independent variable, we would put it in terms of y and pretty much taking the inverse of that function and using that to solve. So in this case, we're not taking that
This is
direction.
different because that was when we were creating the elements. When we were creating the elements, it depended on how we were going to accumulate. All right, so it's kind of, it's
It's
different.
not being changed into like e of y. It's gonna stay as ln of y.
Yeah, but it's kind of like you're talking about a different situation. It's not. This is just something different. That was when we had to create an element, and then we had to make sure that element was in terms of the independent variable. So and then so you had to resolve sometimes for to get it in terms of the independent variable. This is something different because it's just now we're graphing the arc length function. So what you're talking about isn't graphing the volume function, right? You're talking about setting up the volume function. So it's kind of a different question. Okay, so let's just pick a point on here. I'm gonna pick a point. Okay, here's 3, 2.302. So I want you to tell the person next to you what's the meaning of that ordered pair. 3, and that point on this graph over 3, 2.302. What's the meaning of that relative to the function g? So what is that telling us about the function g over there? Go, tell the person next to you. Okay, where's Cameron? Cameron. Yeah? So 3 is, what is 3 in terms of this graph over here? When you're talking about 3 here, how does the 3 relate to this over here? Okay, so it's right here. It's 3. Okay, and so then what is the 2.303? How about Ray? So that this 3 is that 3 there, and then what is the 2.3? The x value of that point? The x value of that point right there? Okay, how about, where's Christian? Or Christy? All I have is Christ. It cuts off all the first names. So it's this Christian, Christy, Woodard. Oh, Christian. Christopher. Sorry.
You can call me Christ.
Okay. 2.302. What does that mean? Okay, from where to where? So where should I start? Where should I start to draw this arc length? Here? Okay, and then to show the 2.302, it would be what? Horizontally, like this?
Oh, sorry, no, you do it at 2.302.
So we're talking about what is the meaning of the 2.302? Arc length. But what does that mean, right? So arc length, you got the right words, but could you describe to me exactly what quantity that 2.302 is? Okay, Nicholas. So you want me to draw and do what? Follow the graph. And tell me where to stop. So the 2.302 is the length of what I just drew, right? So that length is 2.302. Because that's what this is, the arc length function starting from y equals 1, and it's going to tell me what the, as y increases, it's going to tell me what length I've traversed on this graph as y increases. So these are values of y over here, and then these are values of arc length. Does it make sense? Question, yeah? Oh, okay, great.
Yeah, like because 2.302
Uh-huh.
is the amount of arc length that has generated from x equals 1 to x equals 3. Yeah.
Y equals 1 to y equals 3. But then I put the y equals 1 to y equals 3 over here. So this is our y, right? This is our y coordinate, but put on the horizontal axis. Right? So here I am, y equals 1 is here, so 0 arc length, right? 0 arc length. So as y increases up this way, I generate arc length, right? And so that's like, these are the y values increasing this way now. And then the y values over here. These y values then tell me how much arc length I've generated for that much of the y over there. So, talk to me. So, how are you? Is it better? So, is it the fact that y is now x? Right. Yeah. So this is really really practicing like covariational thinking, seeing how quantities change together and how they're represented. Okay. Yes. Question.
It's a little bit like I just lost the word.
I'm sorry.
When you put one function inside another.
Composite.
Thank you. It's like composite functions. You take, let's say you have to do like f of g of x, then you have to find g of x, and that's a y value, right? But then when you go to the function f, that g of x y value becomes an input, and therefore we put it on the tend to put it on the x-axis. It's an input for g. And so what you need to do is you need to think that if we're graphing with respect to y, then we're not inching along here, we're inching along here. So this axis becomes here, and then this length is still the y value length.
Is it better? Can you ask another question? Is there a question back there? Yeah.
So if we're just accumulating arc length, and that's what we're producing on that right-hand graph,
Right.
like why does it matter whether the graph is a function of x or y? The arc length, whether it was the ln of x or the ln of y, would be the same, wouldn't it?
I think so. So if I instead did, all right. So let's call it h. So h of x is ln of x, and so then what would the graph of that look like? Let me. Oh no, what just happened? Undo. Okay, so that would just be the graph then would look like this. Something like that. Yeah, so then if h of x is ln of x, then the x coordinate over here would now be the same as, now we would have the exact same over here. Yeah, you get the same arc length because you'd be drawing it on this, here. But now the x value, this now would be a function of x, and so we would take these x values and just replicate them over here. But now the new y values over here would be arc length, this arc length here, like this. Yep. Other questions? Okay, so let's practice again with number 2, the surface area problem. Okay, so we had gy is 4 minus y squared. And we want to graph that from, hold on a second here. I want to give it away here. Can't get my there, shoot. Sorry. Okay. So this one is gy equals 4 minus y squared, and we're going to take that curve and we're going to rotate it around the y-axis, and that's going to create a surface. It will not create a solid. It's going to be like a surface, meaning like something like a paper plate. Okay. So what exactly will that look like when we take that thing around the y-axis? Can we get a sketch of that? And again, it's not a solid, but so I'm going to take that thing. I'm just going to sweep it around all the way around the y-axis. Can you describe what that would look like? Yeah. Frisbee with a hole in it. That's a pretty good description, right? But that frisbee, what is infinitely thin? Infinitely thin. Okay. So we're going to have a hole up here like this. And this is going to come down to 4 like this. It's going to look like that. But this is not a solid, right? This is not a solid. It's like an infinitely thin frisbee with this hole in the top. And so we want to find the surface area of that thing. Okay, so I need my surface area function, which is the same as we know it uses the arc length, but there's also what? So we're going to, our typical frustrum is going to look like this. Okay, and then what is the surface area of that? Or the rate of change, right? What's the rate of change of surface area of those things? They're like ribbons, right? They're like ribbons, but the edges of those ribbons are angled to match the curve, right? So it's based on ds, right? There's a little ds here. So to get that amount of area, it's going to be what? Remember? So how would I get that little bit of area for that one ribbon? Where is, how about, where's Supin? Supin Zane? Yeah. So what will that little bit of surface area be? 2 pi. So if I draw it here, right? Like that. So 2 pi times, what's the radius of that? What's that? X, right? So it's going to be 2 pi x, good. And that's going to be our perimeter of that thing. And then we're going to take that times the little bit of arc length, not dy, right? So we proved the point last time. It's not like a volume cylinder. It has to be times ds. So what would ds be? Want to keep going? Square root of? Okay, good. Okay, so then we need, so that's our rate. This is our rate right here. Our rate function is all of that. So because we've got our function in terms of y, we're going to use y. So then we need to get that in terms of y. So here's an example of what you were asking about. This is what you were asking about. So what is x in terms of y now? What am I going to put in there for x? Where is Nikita? Is Nikita here? Tell them they're going to learn your names. Where's Jake? Jake. Oh, second time, Jake. All right. So x is what? So r is x, but we need to write that in terms of y, right? We need that x in terms of y. So what will I put there for x? Not sure. Yeah, yeah, exactly. Because that is gy is x, right? And so it equals 2. So I could, yeah, so when I put it in, I can just put g of y since I've defined it that way. That's right. Because that's x, right? X is 4 minus y squared. Okay, so let's see if that agrees with what I did here. Is that what we said? So again, y is going to be my independent variable. So the first ribbon, when y equals 0, is going to be where on the Frisbee? Where's the first ribbon that we're going to accumulate surface area? And where is that on the Frisbee? Yeah. The bottom, right? So y equals 0 is like the rim of the Frisbee, the biggest, that has the largest radius, right? And then as y increases, the ribbons are going to build up from the bottom, right? We're going to be increasing. Yeah. Uh-huh. The whole thing. This is the whole thing. So it's the rate times the little change. So ds is the rate of change of surface area times a little change. Yeah, so this is the rate of change of surface area, and then our ds is our little change in, right there is our little change in arc length. Yeah. Yeah, so think of this. This is the rate of change of surface area, and then this whole thing now is a little change in arc length. ds is this part right here. All of, including the dt, that's all ds, little s. Yeah, that's all little s. Okay, so sketch the graph. Can you sketch the graph of the accumulation of surface area? Just a rough sketch. Okay, and we'll do the same thing we did last time. We're going to put on the new graph what the x, the horizontal axis, which we think of as x, is going to represent the y values, the independent values of in our function g. And then the vertical axis will be amount of surface area generated for that much of y. So what would a rough sketch of that look like? Can you sketch it? And how will I graph that in GC? How will I graph that in GC? So, Matthew. What's up, Matthew?
So that's going to be y is equal
Whose mouth is moving? Whose mouth is moving?
Oh, right.
Okay, cool. All right, so.
Okay, so since we already have the function defined, it's going to be y is equal to sg from the start, which is 0, comma, and then I guess x prime.
So x. All right, so he wants y equals s
Sub g.
g, s sub g of, he wants 0 comma x. What do you think? To graph that over here. He likes it? All right, yeah, that's what I got. And then so rough sketch of that. Can you explain? Did you get a rough sketch of that? Where is Daniel? Daniel T. Daniel here? Okay. So the initial point will be what ordered pair? So an ordered pair has 2 coordinates. So when you say 0, so what would the ordered pair be for the initial point? 0, 0. Okay. So here. Work its way up. but it's going to go up to the right. So something like this, right? Because right, as y increases, we're going to start accumulating surface area. And so as y increases, we're going to start from 0 this way, because y is starting from 0, right? And then it's going to accumulate surface area. And so your y values are going to increase, your surface area values are going to increase as your y values on that graph increase, and our y values on that graph are shown on the x over here. Does that make sense? So let's graph it. We'll do blue. Wrong graph. I need to put it on over here. Okay, why is it going up so steeply, seemingly? Because there's a lot of surface, right? It's way out here, away from the y-axis. It's coming way, it's got this huge diameter of 8, right? That frisbee has a diameter of 8, and that's just generating a lot of surface as it goes around. Okay, so as soon as you start coming up, you're generating surface quickly. So let's zoom out, make it look a little. Okay, so take a point, interpret it. So here's the point. Oh, there it is. 0.5 and 14. 0.5 and 14. Interpret the meaning of that point on this graph over here. 14 and, 0.5, 14. Go. Tell the person next to you. What does that point on that graph mean? Okay, Alec, you're up. What do you think? What you guys talk about? Okay, so GY, looking over here, as you go from 0 to y equals 0.5 over here. So does that show up? Oh, barely. Black. Okay, there. So there's as you go from 0 to 0.5. So it's this much right there. Is that what we're talking about? But what? Not that arc length. Yeah, but so that little piece. So from 0 to y equals 0 to 0.5, you get that much arc length revolved around the y-axis. It's going to give you a little bottom strip of the frisbee. And that bottom strip of the frisbee has 14 square units of surface area. If we were up to 0.5 and y. Okay, your turn. Just pencil. See how we do. When they get to the back, you're going to pass left and right. I did not count. Hold your hand up if you need one. If you got extras, look for a hand. Do your best. Work hard like it's all of your grade. Yeah, pencils down. Okay, here's the arc length function. Just put your pencils down. Just put your pencils down. Pencils down. Okay, so as long as you show it going up from x equals -1, that's good. Bonus, if you actually showed it flattening out a little bit, that's bonus. Okay, good for you if you got that. But if you just show it up and to the right, that's fine. Okay, and then that point would mean it would be the arc length from -1 to 1. So it'd be, here's y equals -1, the length of this arc from here to here. So if you shaded that right there, up until y equals 1, that's what that 3.927 is. It's that much arc length. And then the last question would be what? 1/2 of s sub k of -1 to 5. 1/2 of s sub k of -1, 5. That would be the last answer. That'd be half of all the arc length.